Hello, and welcome to the Current Science and Technology podcast from the Museum of Science in Boston. I'm your host, Susan Heilman, and every week we bring you interviews with guest researchers and our museum staff covering science and technology in depth. This week, we'll talk about very tiny medicine. I have with me Dr. Jim Wilking, a physical chemist at Harvard University, who's here to talk about his research developing teensy tiny drugs. Hi, Dr. Wilking.
Hi.
You're a physical chemist working on drugs, but why teensy tiny little drugs?
A lot of drugs don't dissolve very quickly in water, and this is an increasing problem in pharmaceutical sciences. And one way to increase the dissolution rate of drugs in water is to make the drug particles very, very small.
Now, why do we care about drug particles dissolving in water?
Well, so it turns out most drugs are delivered in pill form. So you swallow them and they dissolve in your stomach. In order to access your bloodstream, the drugs need to dissolve. Your stomach acid is essentially water is an important thing.
Okay. So when you're out of the body, you don't need to use stomach acid. You can just dissolve it in water.
Yes, although we mimic stomach acid.
So making a drug very, very small makes it dissolve easier in water.
Yes, yep. So if you take a particle and you, say a sugar particle, and you put it into water, the rate at which that particle dissolves will be proportional to the surface area of the particle. And if you take that particle and you crunch it up into smaller and smaller particles, you'll increase the surface area. And since you're increasing the surface area, you can increase the rate at which the particle dissolves.
And the faster a particle dissolves, the faster it'll get into a person's bloodstream and start actually working in their body.
Right, yep.
Okay, so how do you make something very, very small? You mentioned sugar particles. You can just grind up sugar particles. So does that work with grinding up a pill?
Yeah, so it does. So, and that's kind of been the prevailing technology for the past 100 years, taking crystals and grinding them up using a mortar and pestle or any kind of mechanical means that you can imagine. There are certain problems with that. In a lot of cases, you can't get the particles very small because as you really smashing these particles, you end up smashing them together if you apply too much mechanical energy. So you get agglomeration and kind of coalescence of these particles.
Can you damage the particles if you pound them too much?
I don't think you can damage the chemical nature of the particles, but you can do things like incorporate impurities into the particles.
So if you're not using mechanical energy to grind up these particles smaller and smaller, what are you doing to make them small?
So there are a lot of ways of doing this, and there are a bunch of people that are working on it. I would say next to mechanical grinding, this is not what we do in our lab, but next to mechanical grinding, probably the most common way of getting really small particles is to take a drug that's dissolved in an organic solution to allow it to precipitate or cause it to precipitate somehow. So you're going from molecules in solution that are now precipitating out as crystals, but you want really small crystals, so you arrest the crystallization process as it's occurring in the early stages. So initially you have these really tiny crystals that are nanometers in size, and they grow into tens of nanometers and then hundreds of nanometers. And if somewhere along that process you can arrest the crystallization, then you kind of have these really small particles, and you have what you want.
Okay, because in solution they're usually individual.
Yes, in solution they're individual molecules when they're dissolved. Yep. But so the problem with that technology, it's a beautiful technology and it's useful, but the problem with that is that you need to add surfactants or detergents that will stabilize the growing interface of a crystal. So you mix these in with your drug, or at the appropriate time you add this surfactant, and the surfactant goes to the surface of the growing crystal and stops its growth, basically. The problem is you need to tune your chemistry when you do that, and so for each of these drugs you really need to optimize what your chemistry is and pick the appropriate surfactant.
Okay, so what is your way and why is it better?
Well, so the way that we do it is we take, it's actually a really simple method, and I'm completely surprised every time I talk about this that no one has done it before, or that no one had done it before. But it's just to take really small particles that you can get really cheaply, these really small glass spheres that are dispersed in a liquid, and you pack them together very densely, so that if you think about like oranges or something, or apples in the supermarket that are packed together very densely, they're not filling volume completely. There's this space between them. In chemistry you'd call it interstitial space between atoms. In produce I don't know what they call it, but there's this space between oranges. And you have the same thing when you pack together small spheres that are microscopic, you have the space between them. So if you use glass spheres that are slightly smaller than a red blood cell. Say a red blood cell is 5 microns. You use glass spheres that are 1 micron, and you pack them together densely. The space between those spheres is about 160 nanometers in size. The size of the interstitial space is 16% of the size of your packing spheres.
Okay.
So 1 micron gives you 160 nanometers. 100 nanometer packing spheres gives you 16 nanometers.
Wow. So you get these already made, not too hard to make, cheap to make glass spheres.
Yep.
And they're in water.
Yep.
And you just dump in the drug and it fills in all the little spaces.
You have these spheres that are packed together, and you suck out all the water, so you get rid of all the water, so you just have air in the space. And there are a variety of ways that you could fill the space with the drug. If you want to get the drug into the space. Well, I'll talk about our way, which is the simplest way, is just to take drug and melt it. So you take a solid drug, you melt it, it becomes liquid. And the neat thing about glass is that it has a high surface energy. That means that a lot of liquids, almost all liquids, want to wet the glass. So since you have these small spheres that any liquid will wet them, if you put liquid in contact with that packing of spheres, it immediately sucks the liquid into it.
Cool.
So the way that we do the process is I just take a hot plate, I take drug, I melt it on the hot plate, and I put one of these sphere packings on top of it, and the sphere packing imbibes the liquid drug into the space.
So now you have the glass beads, but in between all of these glass beads are these little teensy tiny nanomedicines.
Yep, yeah.
So then how would that be delivered? Do you have to remove the glass beads first and then ingest that? Or can you ingest the glass beads?
So glass beads silica has been approved for drug delivery for quite a long time. So that's no problem. You can ingest these small spheres, and apparently they're compatible with your body, and they don't do any harm to your intestine. So there's some neat physics that came out of this problem that we didn't expect. Now you have this composite. You need to somehow leach away the sphere so that you can expose the surface of the drug to whatever liquid you want to dissolve it in.
Right,
so you need to get rid of the sphere somehow. The neat thing is that you don't need to do that, because when you take this composite and you drop it into water, the water itself penetrates into the composite and splits the drug away from the silica. So it breaks this whole thing apart, and the composite basically disintegrates. And this was something that was completely unexpected and super cool. So we can skip this leaching step and deliver the composite.
Cool. And then inside the body, as it hits your stomach acid, it just will break apart, and you'll be left with these little teensy tiny drugs that is much easier to be able to disperse throughout your body.
Yep, that's right.
So the goal of all this is to get your drug in one of its smallest forms possible.
Mm-hmm.
So we take most of our drugs in pill form. Why not take it in liquid form?
So that's a really good question. I started this project as a chemist and not as a pharmaceutical scientist. And that was one of the first questions that we had thought about this. You thought, well, why not just dissolve this in some kind of organic liquid, right?
Yeah.
One of the problems there is that one of the most compatible organic liquids that you could drink is ethanol. And, while you may enjoy drinking ethanol, you might not want that in combination with your drug. And there might be some kind of side reactions. So I'd said before that the rate at which these things dissolve in water is very slow, but they also have a very low solubility, which means that you can't get very much of the drug into water.
Okay.
So yeah, you could imagine kind of pre-dissolving the drug into water beforehand and then drinking that water, but you would have to drink a whole lot of water in order to get enough drug.
Okay, that makes sense. And so overall, it's probably easier to ingest a pill. You can get a lot more concentrated drug. Yeah. In this type of pill format that you're talking about, with lots and lots of surface area of the actual chemical we want to ingest.
Yeah.
Well, thanks for talking to me about your research with teensy tiny little drugs and your work to actually make them that small.
Thank you.
That's it for this week's show, but be sure to come back next time for more of the latest in science and technology. This podcast is a production of Current Science and Technology at the Museum of Science in Boston, part of the Boston community for over 175 years. For more information, visit our website at www.mos.org/CST or email us at podcast@mos.org. Thanks for listening.